So the topic of our conversation today is Postgres performance for application developers. I probably need to re-emphasize that this talk is focused towards application developers, and if you are already a database expert or a Postgres expert, you will likely know of all or most of the concepts that are going to be discussed over here. But the key point over here is there is no magic button, which is why we need to understand these concepts. My name is Umair Shahid, and if you do a select star from me, this is what you get. I have flown in from Islamabad, Pakistan to give this talk and do a few other things in the region. And I've been working in the Postgres space for more than 20 years, started off in 2003, and have spent time with major Postgres providers. Started off at EDB, went on to OpenSCG and Second Quadrant. Second Quadrant got bought out by EDB, so right back to square one, and then onwards to Percona. And now I'm running a professional services organization focused on Postgres by the name of Stromatics, with the mission to help businesses scale Postgres reliably for mission-critical data. But that is not what we're here to talk about. So the idea behind this talk is to enable and empower developers to be able to leverage the Postgres database in a way that will help applications scale, in a way that when they bring their database to DBAs, the DBAs won't smack their own faces. And to help ensure that there is a longevity in the life of the applications, and as users and data increase, the database can keep up. Now, what we're going to cover during this talk is how the adoption of Postgres is expanding all over the world, how the cloud providers or the move towards the cloud is driving most of this adoption, the difference in kicking things off or starting off an application and actually scaling it in production. And then we're going to cover 4 broad areas for scaling Postgres, those being query and SQL optimization, performance features of Postgres, some architectural improvements that you can make, and configuration parameter tuning that is easy and intuitive to do. Now, I created this graph with the help of 2 popular and well-known publications. One is DB Engines, which as database experts and folks in Postgres, we're very keen on quoting because, well, Postgres tends to be the DBMS of the year pretty often, and it was the DBMS of the year in 2023 as well. But what I've done is I've cross-referenced DB Engine's rankings with the developer survey that Stack Overflow does on an annual basis. And I've tracked, so I took the top 5 databases from DB Engines, and I tracked their popularity over the course of 5 years based on Stack Overflow's data, and this is the graph that resulted in it. So Postgres was pretty popular to begin with. So if you go back 5 years, it was still, it wasn't number 1, but it wasn't too bad. It was at number 2. And MySQL had a pretty big lead over the other databases at number 1. And as the years progressed, we see that pretty much every other database is on a declining pattern, Postgres being the only database that is on an upwards trajectory. In 2023, reaching to be the most popular database amongst application developers. Now, the key thing over here is that the way DB Engines tracks popularity and the way Stack Overflow tracks popularity are 2 different KPIs and 2 different measures, while DB Engines is focused on database admins and in general database discussions, Stack Overflow is focused on application developers. So let's combine this with this study that Gartner published in the beginning of 2023 I don't have the updated version that I'm sure Gartner must have published for earlier this year as well. If somebody has access to it, please do share. But I'm fairly certain that it's going to be very similar. There are a few key things to notice over here. One is databases showed a 14.4% growth. That equals to an $11 billion gain for the year. And 98% of this growth actually happened in the cloud. So the 98% out of this 11 billion gain took place in the cloud, and 80% of that cloud is covered by AWS, Microsoft, and Google. So interesting stats over there. But what this shows is, A, Postgres is now extremely popular, or the most popular amongst application developers, and most of this development, most of this deployment is taking place on the cloud, right? And then the question becomes, what do you do when you want to scale Postgres in the cloud, right? And there's a simple answer to it. Swipe your credit card, right? That's what everybody wants you to do, right? You swipe your credit card, you get a bigger machine, and there you go. You have scaled your Postgres instance. But you know what? What you actually end up doing by swiping your credit card is you're just delaying the inevitable. No matter how big of a machine you get, you are going to eventually run out of resources if your database is not designed properly, if you haven't architected your solution that is meant for optimized execution. So that may not be the best solution, even though it might sound very intuitive. Now, another aspect over here, as applications are developed and tested in sandboxes and, well, other test environments, this is kind of what the test environment looks like. You drive a race car over here, you can test it out, you can really test out the cornering and the speeds and the bursts and handling, et cetera. But production actually looks like this. This is an actual picture from my hometown, right? And believe you me, if you're stuck here, it doesn't matter how fast your car is, you're not going anywhere. So yes, your fast car probably performs really well on this track. It won't do anything here, right? So in order to make sure that you're able to leverage the power that you have from your machines, from your database, there are many different aspects that need to be optimized. And unfortunately, this button does not exist, or at least I haven't found it so far. If somebody has found it, or if somebody knows how to access it, please let me know. But usually, as we work with our customers, as we work with clients, this tends to be what people are looking for. For some odd reason, each time somebody comes to us with a performance problem, the question usually is, but there must be something that I can just switch on and everything is going to be fine. There must be some tweak that I can do to make everything better. And that's what this, this unicorn-like button is that people tend to be searching for. It doesn't exist. I don't know where it is, but we cannot rely on make everything okay. And hence, we come to the 4 aspects that I want to talk about during this conversation today. And those 4 aspects are focusing on optimizing your queries and SQL, certain performance features that you can leverage within Postgres, the architectural improvements that you can make in your Postgres deployment, and some parameters that you can tune. Again, the important aspect over here is that these are high-level abstracted concept that I'll be talking about today, easy to understand, easy to use. You don't need to be a guru in databases to be able to do this. Application developers are very smart people. Very easily, this is stuff that that developers can handle. You don't need database expertise, or you don't need DBAs to be able to do this. But it is important to take care of some of these things. We'll start off with query and SQL optimization and go through a few basic tips and tricks that you can leverage. The first thing that I'd like to share is about pgstat statement. Now, this is an extension that is included in the Postgres distribution. So if you're using Postgres, if you have deployed Postgres, even if you don't know about pgstat statements, let me assure you that it exists on your system. It exists with your database. And what it provides is a view into statistics of SQL statements that are being executed in the database. And typically, when we start analyzing a slow-performing database in any production or any customer environment, there are two key factors that we look at. One is what queries are taking too long to run, longest running queries, and the second is which queries are running very, very frequently. So the reason behind the first, of course, is that if there are queries that are taking too long to execute, you want to make sure that you optimize them. And if there are frequently run queries, you want to make sure that they're as efficient as possible because they are being executed very, very frequently. And in pgstat statements, you can take a look at mean execution time for longest running queries. This will give you an insight into what queries are taking a long time to execute, and calls to take a look at which queries are being called most frequently. And two other interesting stats that you can analyze and look at in pgstat statements are standard deviation and I/O intensity. Standard deviation because if a query is taking very long to execute at one point in time and it executes very quickly at a different point in time, there's something wacky going on. It probably needs some investigation. Query performance should be fairly consistent, and if standard deviation is big, something needs to be investigated over here. And I/O, well, it's an expensive operation. It takes a round trip to the disk, and that round trip is expensive. And if there are queries that are I/O intensive, you want to try and see if there is a way to optimize them such that they leverage cache, some that they leverage the memory availability and minimize the trips to the disk. And a couple of things to watch out for when using pgstat statements. It is off by default, which is also why a frequent occurrence that we come across is we ask a customer, hey, have you turned pgstat statements on? And they go, what is pgstat statements? So it's off by default, which means that if you don't know to look for it, you will probably not know that it exists. So you need to turn it on. And secondly, the data is aggregated from the time it was turned on or from the time it is reset. So you don't have the ability to time bucket the data with pgstat statements. It's accumulated data. And there's a small CPU overhead when pgstat statements is turned on. It's approximately 4%. This is based on a few studies that have been published and based on best practices. The overhead generally is small enough that it is negligible, and the benefit far outweigh the small overhead. Some tooling that you can use to visualize and to analyze this data better. pgadmin gives you the ability to visualize and in a GUI interface give you access to pgstat statements and to visualize that data. pgbadger doesn't use pgstat statements directly. It analyzes the log files, but it gives you very similar statistics, and it's a tool that will help you visualize through graphs and charts of how your queries are performing and how your SQL is running in the database. A combination of Prometheus with Grafana, Prometheus using Postgres exporter to export data and to export these statistics, and Grafana to help you visualize can also be an option. And if you're willing to go towards commercial tools, These are some of the popular tools that we have seen used in production pretty reliably. You can use Datadog, dbeaver, or New Relic. There are others as well. This is just an example that I have put up. Now, moving on from pgstat statements, talk a little bit about explain plan. Now, the way Postgres Query Planner works is that it does a cost-based analysis of the different ways a query can be executed in the database and which plan is the least costly. Right? So think about you need to buy something. You will research as to the specifications of what you want to buy, but you would also research as to where you can get it cheaper. Let's say you're buying a television. You've already decided what television to buy. You will probably want to buy it from the cheapest source because, well, you don't want to spend money. That's what Postgres wants to do as well. Doesn't want to spend a whole lot of resources on executing the query, so it assigns cost to different resources that are available to it, including CPU and memory and I/O, and based on the cost of executing a particular query, it decides which plan to use. I'm going to elaborate on that a little bit and help you understand what these costs are and how to control them. But broadly speaking, it's two things that are involved in deciding the cost of execution of the query. One is based on configuration parameters that will help the query planner determine how much cost is going to be involved for example, fetching an index, seeking data from memory versus seeking it from disk, how expensive a sequential scan is going to be versus an index scan, etc. And the query planner also gathers statistics from the database in order to understand, for example, an estimate of how many rows a table has, how wide a column is for a table. And based on these statistics and configuration parameters, it then calculates the cost of executing a query. Key metrics in an explain plan, I'll come to an example in just a bit to help you visualize what this all means as well. But key metrics that you want to watch out for in an explain plan are cost, rows, and width. Cost, of course, is calculated by the query planner. It's not an absolute number, so don't read it as the number of milliseconds that the query is going to take, or the number of seconds, or in any way. It's a number that is relative in its nature, and the query planners use that relative nature to determine which cost is higher versus lower. The number of rows a query is going to return, and the width of each row that the query returns. These are the key metrics to watch out for in an explain plan. Now, the key outputs that an explain plan gives you are how it's going to scan the data, how it's going to join the data, how it's going to aggregate it, and how it's going to sort it. Right? These are the four key areas that it does. The way you run an explain plan is that you type in explain, and then you add the query in front of it, and that will give you the plan for that query. If you do an explain analyze, it will not only give you the plan for the query, it will also actually execute the query. So if you want to find out how long it's going to take to delete all the data from your database, do not do explain analyze, please. Right? Okay. Now, an example. Just a random example, nothing very specific about it, but 3 tables involved over here, order details, and products. And what we want to do is we want to understand what are the top 5 selling products of 2023 and what their sales looked like. So we pick up the product name, we sum up the multiplier of the quantity and unit price of the total sales. We join order and with the product ID between the product and the order details, and we group by product name. The where clause talks about the whole year of 2023. We order by total sales, and we limit by 5. So this will give us the top 5 sales or top 5 products by sales for the year. Now, if we run and explain on this, and the tables are currently not indexed, if we run and explain on this query, this is what the output is. Now, it looks like a bit of a scary output. If it's your first time looking at an explain plan, it's a little hard to decipher what's going on over here. There's a lot of words and numbers in there. But let's just go back to what we talked about in this slide. 3 things that are the key metrics in an explain plan: cost, rows, and width. And what you need to look for are scan, join, aggregate, and sort. Now, let's look at the cost, rows, and width. There's a cost label in pretty much most of the rows, and within the parentheses, you've got rows and width. What this is saying is that the startup cost is 0, and the total cost to execute the sequential scan is 225. 2,000 rows are going to return, and each row is of 8 bytes. Essentially, that's what it's saying. So these are the 3 things that you need to watch out for: cost, rows, and width. Now, the reason why I say that you need to watch out for is that if at any place you find that the cost is turning out to be too high, or the number of rows that this returns is higher than you expect, or the width of the row that it returns is higher than you expect, then there's something wrong with the query. Let's say you expected the query to return 1,000 rows, and the explain plan shows that it's actually returning 10,000 rows. You're retrieving more data than you absolutely have to, which will impact the performance, which will make the database go slow. So you want to make sure that that doesn't happen. This explain plan is it's nested. So the innermost segment is the one that is going to execute first, and then it goes upwards. So when the startup cost of this guy over here is 0, and it goes on to 225, this is where the hash starts off. That is one nest above it, and the cost is pretty much 0, and so on and so forth. Now, these 3 things: cost, rows, and width, and the way it scans the table, it's all sequential scan over here. The way it joins the different tables, and the way it aggregates it and sorts it. These are the key things that you need to watch out for. Now, the why you need to look at how the query planner is scanning the database or the table is because, well, if the columns are indexed and explain plan shows that it is doing a sequential scan, there is something wrong going on. You want to investigate that, and you want to make sure that it gets fixed. So look at the explain plan. Look at anything that might be wacky in there, but what you want to really focus on are, again, this is very important, and that's why I keep emphasizing, is cost, the number of rows returned, and the width of each row that is returned. Now, in order to help the query planner do its job properly, it's important that analyze is run periodically on the tables. What analyze does is it updates the statistics of the particular table. Let's say there's a table in your database that is updated very frequently, that has a high level of insertions. As the query planner plans queries to execute on that table, you don't want it to assume X number of rows, whereas now there are Y number of rows where Y is significantly higher than X, because then the planning is going to go haywire. Running analyze on the tables periodically helps ensure that the database statistics are kept up to date. And in order to help the planner calculate the costs accurately, and this is the cost that we were referring to as an arbitrary or a relative number. The database parameters, the configuration parameters are there for tuning. You can adjust these parameters based on your workload and the hardware that is available to you, and we are going to do a little bit of a deeper dive into the database parameters in just a little bit. So don't worry if you don't yet understand what this means over here. Now, moving on, another thing to watch out for, very simple concept is watch out for locks as you program and as you write the SQL code. The simplest example that I could come up with, let's say there's one session that starts off a transaction, it updates the table foo, and it sets the value of ID 1, 2, and 3, and then commits it. Session 2 is also updating that same table and also tries to update ID 1. Now, while session 1 is taking place, it has locked ID 1, the row with ID 1, because it has updated it. And till the commit happens, it will keep an exclusive lock on that row. And session number 2 is going to wait for that lock to be released before it can execute its statement. Now, you want to make sure that such exclusive locks are only used when they're absolutely required. And this is especially critical for long-running transactions, because a long-running transaction could hold on to an exclusive lock for a long time, and which will prevent other processes from updating that same table, thereby impacting the performance of your database. So key takeaways from SQL and query optimizations. Monitor your queries. Make sure you're on top of them, that you understand which your longest running queries are, what your most frequently run queries are. Analyze how those queries are being executed to be aware of any anomaly, anything that looks wacky or off, and code in a way that avoids locks. Key takeaways. Now, the next point that I'd like to discuss are some performance features that Postgres offers. And mostly, I would want to talk about indexes over here. Now, Postgres offers different types of indexes that you can leverage based on your use case, based on how you want to query the data that is in the table. The default index, if you don't specify anything, the default index is the binary tree index. And as is evident from its name, it structures the data in the shape of a binary tree, and can be used for equality access. It can be used for range. It can be used for greater than, less than, et cetera, et cetera. Hash indexes are focused on equality checks. So essentially, it stores the hash of the key, and it can do a very fast lookup for an equality check. Now, a hash index is really bad for range comparisons, which is where the B-tree index shines. So this is use case dependent. A hash index should be used when you need fast equality access. A composite index is multiple columns combined, which is used when you have queries that frequently access data where the conditional clause is dependent on multiple columns. So if your where has not one, but two or more columns involved in it, having a composite index on all of those columns will help that query retrieve data faster. A partial index is not just on the column, but there's a conditional statement or a conditional expression that it evaluates. It makes the index smaller in size. It doesn't index the entire data. It only indexes the data that satisfied the condition of the expression. A covering index is used, well, there's a very slight difference between a covering index and a composite index. A covering index also captures multiple columns, but this is used when you don't want your queries to hit the table, you only want your queries to retrieve data from the index. The way it's defined is you define an index on a particular column, and you use the include keyword for some of the other columns that you usually retrieve data from as well when you query a conditional clause for column A. So let's say there's column A where the index is being implemented, and you as a routine also call column B and C in the select queries. If you include B and C in your covering index, what Postgres will help you do is when you query that particular table using the index, it will retrieve data from the index, not from the table, thereby saving you time and giving you better performance. Brand index, short for block range index, essentially what it does is it stores the minimum and the maximum values from the page size and not the entire data. So essentially, for very large data, which is spread across multiple pages, it will help you save a lot of disk space. It only captures the minimum and maximum values on a single page, and then it can zero in very, very quickly into a value that you might have queried. Now, with indexes as well, it's not a one-size-fits-all. So be careful as you use your indexes. Indexes do take up space, and they will cause bloat if you overuse them. So please don't overuse them. And a few conditions where indexes are probably not recommended. If you need most of your data anyways, Postgres will end up doing a sequential scan on your table, and the index is just going to be not utilized and wasted. You're wasting disk space. If you have a very heavy write or update workload and very few reads, index is not going to be used. And each time you insert new data or update data in your table, the index will need to be updated as well, which means that you're actually slowing down your database while not leveraging the index functionality. So for write-heavy workloads, update-heavy workloads, and workloads that have very seldom reads, indexing is not a good idea. We have already talked about data bloat. If your table is too small, and a sequential scan will just fetch it very, very quickly, no point in inserting an index in it. And a few highlights, and these are just examples. There are many such examples in Postgres. Performance features that just work. You really don't need to do anything to invoke these features or make them work. Postgres is intelligent enough to, for example, plan for parallel query execution, leveraging the multiple cores that are available to it if it can. It will avoid index changes using heap-only tuples if you are changing a row that or in a way that is not impacting the index or that's not updating the indexed column. It will use heap-only tuples to avoid the index updates and thereby improving the performance. Incremental sort, if data is semi-sorted, Postgres will not just start from scratch and sort the entire data. It will intelligently leverage the semi-sorted nature of the data and help sort it faster. Auto vacuum, I know at least yesterday there were a couple of talks that were focused on MVCC and auto vacuum. So as updates occur and as dead tuples increase in the table, the auto vacuum process will kick in and automatically clean up the dead tuples, thereby saving you table bloat and getting rid of all the dead tuples. Now, all of these things happen automatically. All Postgres asks you to do is to let it do its job, and it will do it. So you don't need to tinker with anything. You don't need to invoke anything. Yes, Harry?
You do, actually. If I can comment. For parallel queries, there are two parameters, which is max parallel workers and max parallel workers per gather. And you need to optimize them for this feature to kick in. So you need to do something.
So yes, but you can optimize them. You don't need to tinker with them for this to kick in. Even if you don't optimize them, Postgres will still execute queries in parallel with the default values.
Yeah, sometimes
Right.
you're going to, okay, that's a separate story, but most times you actually need to touch them.
Right. So yeah, optimization definitely. I'll come to optimization in the next section. There's lots of optimizations that you can do. I completely agree. There are parameters that will help. There are parameters for example, auto vacuum as well, right? That can help optimize how auto vacuum is done. But the point over here is that you can go into that if you know what you're doing, which of course you do, Harry, but not many people do. So key takeaways from the performance features that you can leverage. Indexes are a powerful ally, but please don't overuse them. And let Postgres do its job. Don't tinker with it too much. It will, for the most part, very intelligently figure out the best way to execute queries. Now, the next point is architectural improvements that you could possibly make in your database. And the first aspect of it is load balancing. And what load balancing does is essentially it distributes queries across multiple nodes or servers in order to make sure that one node is not overutilized or is not burdened with all of the queries and all of the transactions that are taking place. The benefits are it prevents the single server to become a bottleneck. It can facilitate horizontal scaling. And, well, the byproduct is, well, while we're working on performance, but the byproduct also becomes, the system overall becomes resilient to disasters because now you have multiple copies of the data, and in case one of these nodes break down, you can fail over to the other node. Graphically speaking, this is roughly what it looks like. So on your left over here is a single server that is serving the application, which is writing and reading from it. And that same database is serving the reporting and analytics for the business. Now, all of the write and the read workload from the application and from reporting and the analytics have to be handled by this one node, and the node can be overwhelmed. We had a very interesting example recently. Again, this is back from my hometown. I was working with a team that is monitoring. Well, a little bit of context actually before that. So Pakistan, unfortunately, is one of the very few countries left in the world that still is endangered by the polio disease, the crippling disease, and there's a massive effort ongoing in the country to vaccinate and immunize kids against the disease. And there are campaigns that are run. And we were working with the organization that is tracking the administration of those doses to all the kids in the entire country. And what they were doing is that they were using the cell phones of all the workers that were going door to door all over the country and tracking their location pings, storing their lat long, and creating heat maps in a central location to determine where the workers were actually going and what parts of the country they might have missed. Right? So lots of data streaming in, and a very nice dashboard built up to create a nice decision-making environment. And they came to us, and well, that the entire data was being stored in Postgres. Now, they came to us saying that when they start running analytics on the data that's coming in, the rendering on the screen for the real-time pings that are coming in from the field, that slows down significantly. Right? I actually went into their office trying to determine what was going on. Now, this was a team that had really good engineers, good skills within the team. But one thing that I found surprising was that all of these transactions, all of this processing was being done on a single node, on a single server. So lat long pings from all over the country, from all the workers going door to door, coming into the same server, all analytics being run on the same server, and when the management wanted to run some reports, the pings coming in, the database would just refuse to ingest them. Right? And this is what we recommended. What we said was, let's load balance your database. So you'll have one node that is dedicated to ingesting the data, and we can set up replication to 2 standbys, and the application that is sending those pings, whenever it needs to read the data, can pick it up from standby 1, and you can run your reports on standby 2. And just splitting that load helped decrease the pressure on this single server, and then everything just started working fine. So load balancing can be a very interesting trick, or a very simple way to elevate some of the pressure, reduce some of the pressure that one node might be feeling if your workload is both read and write, and there are different parts of the business that are doing different kinds of stuff with the same database. You might want to split the database up to serve those different parts of your business. A simple example that I came up with, actually, this was a quick hack into my own laptop using pgbench. Just run 3 nodes on the same laptop versus 1 node on the same laptop. For 60 seconds, run a select-only pgbench run. And even on this very, very simplistic measure on the same hardware, we could see performance gains where the TPS was about 371 for a single node, and it went up to 485 for 3 nodes. Again, now the hardware is the same. It is running on the same hardware. The resources for 3 nodes combined over here and 1 node over here was the same. And even then, Postgres was able to perform about 30% better when the load was distributed. So this is one easy way to improve performance, load balance it. Another way to, or another aspect to look at is partitioning. And what partitioning does, it divides large tables into smaller and more manageable pieces. And the benefit that you can get is that queries are going to perform better, maintenance is easier, and indexes also perform better and are smaller. An example, again, visually speaking, let's say you've got an application that writes time series data, and you have data for the entire year. One way to possibly partition it is by quarter, which is what is being done over here. So think about these 4 partitions as the first quarter, second and third and fourth quarter. Now, if you run a very simple query that is select star from foo, where month is August, what the application does is it queries this database right here, and it needs to scan the table and pick up the data from August. Whereas if, and this of course can be a very huge table, whereas if you use partitions, when you run that same query, you can zero in on the third quarter, and you're now dealing with a much smaller table, much smaller partition over here instead of the larger table, and you will significantly improve the performance of your database and of your queries. Key takeaways from architectural improvements, well, it's just one takeaway. Don't overload a single node. If the node is being overloaded, split it up, scale it horizontally, split up your database. The last point is parameter tuning. Now, we have hinted at this earlier in the presentation. There are configuration parameters that you have access to, and you can change them in the database. For the most part, however, defaults tend to be good enough. Okay? And very broadly speaking, you can categorize the available configuration parameters into allocation, how much memory or resources get allocated to the database, and defining of costs to help the query planner. Now, 3 examples of easily tuned allocation database parameters. The first one is shared buffers. And what shared buffers define is the amount of cache that frequently accessed data can use in the system. The default is set to 128 MB. Usually, the recommendation is to set it somewhere between 25 to 40% of available system memory. You do want other processes to be able to access the memory as well. But the shared buffers is going to define how much cache memory the database is going to use. Wall buffers, write-ahead logs. Again, this is something that other people have talked about, the write-ahead logs. So I won't get into a whole lot of detail about what these are. But essentially, before data is written to disk, it is in memory in buffers, and the amount of data that the database is going to hold in memory before writing to disk is defined by wall buffers. Default is set as 3% of shared buffers, and in high concurrency workloads, raising the value up to 16 megabytes can improve performance. Work memory is the memory that is available for a query operation. So this is a single operation or single atomic operation within a query, or the memory allocated to a single atomic operation within a query. The default is 4 megabytes, and with very high I/O activity, an increase in work mem can probably help because much of that can be done in memory. But you have to be careful while setting it. Too high a value can flood the memory with lots of queries because every parallel transaction that is taking place is allocated this amount of memory. So 4 megabytes is the default, and you can set it a little higher based on the amount of resources available in your system. 3 examples of parameters that define the costs for Query Planner. The first one is CPU tuple cost, and essentially it defines the cost of processing a single row of data. And this includes the wheres and joins involved. The default is 0.01. And a lower value indicates that the cost of processing a row is very, very low, which encourages the query planner to process more rows together. And it's helpful for I/O-bound operations where the bottleneck is actually disk I/O, not CPU. So CPU is used more in case the CPU tuple cost is low. In case the CPU tuple cost is high, the query planner tries to use less rows in memory, and it tends to be more I/O oriented. So if your system or if your setup is CPU bound, if CPU is the resource that you're lacking, you can set this higher, raise the cost, so the planner tends to process low rows, less number of rows, and help with the operations. Random page cost defines the cost of accessing a random value within the database. The default is 4. A lower value implies that random access is cheap, which is good for SSDs, and it encourages index scans. If you have a magnetic drive, a spin drive, a higher value is probably more suited because it is more difficult to access random values in a magnetic disk, and it thereby encourages sequential scans, which are easier to do on a spinning disk. Effective cache size, it's not exactly a cost parameter, but it's worth mentioning because this is what the query planner expects in terms of the cache size to be available to it, and it combines shared buffers and OS cache together. The default value is 4 GB, but the point to note over here is that this is not an allocation. This is an indicator to the query planner as to the amount of cache size that is available to it so that it can plan its queries accordingly. Higher values, of course, imply that there's more data that can be put in cache, and that encourages index scan because you can very quickly access it. And lower values imply that there's less data in cache, so you might need to go to the disk, and it encourages sequential scans. Some takeaways from parameter tuning. you want to tweak your parameters based on not only your hardware, but also your workload. So you want to know what resources are available to your database, and you also want to know what to expect in terms of the type of workload your database is going to be processing. And you will need to experiment a little bit, especially with the cost parameters. You will need to experiment a little bit before you can fully optimize your database, which also makes parameter setting a very good candidate for AI-based tuning. And there are, at least a couple of startups that are working focused on Postgres on AI-based tuning, and I find those projects very, very interesting because this is actually something that, as consultants, we use up a lot of time on, and I think that this can be automated. So it's good that a few people are working on it. Pretty much moving to the conclusion, database performance, there is no magic button. Don't look for it. It involves a lot of variables, and some of them are fairly easy to tackle. You don't need very deep database expertise to be able to tackle them. Tweak those areas, leverage your database to the fullest, and only once the database has been leveraged to the fullest should you think about using your credit card as you scale. Brings me to the end. The QR code is my LinkedIn profile. Connect with me on LinkedIn. I'll be happy to connect and talk about Postgres. And in case you are running into problems, you can just call us. And of course, keep calm. Any questions?
Questions?
To enhance my understanding of the difference between a composite and covering index, you said the covering index is useful because you've added these rows and now you can retrieve, or columns, and now you can retrieve those columns from the index rather than the table. In a composite index, can you also do that when, if I have 3 columns in my composite index and those are the only 3 I'm querying for, do I get those out of the index in that case too?
So you can say that the composite index does everything that a covering index does, and a little more. So with the composite index, each of the columns are sorted in order. A covering index will only sort by one column and include the other columns. So yes, you can use composite index. Sorry? In the index. Sorry? I don't quite understand that point.
So the difference between the two is that the include columns are only included in the last level, the most bottom. The index of each is like that.
Right.
The include columns are only included in the bottom.
Okay. Yeah.
So you do get the benefit of that. Why we don't always use the other index?
Right.
Is because then the index is small.
Right.
Because the data pages the include values are only at the least level of the
Right. Yeah. Exactly. Yeah.
Passing through the top pages is much faster. If you don't need to filter on the other pages. You do have cases where you filter both and include it, so it's possible.
Right. So basically, composite allows you to filter by each of the column, right? And the covering index is filtering by one column, and the other data just happens to be in the index as well.
What is the overhead difference like there? Like how, is if I'm only worried about 2 columns, is it worth it to use a covering index? Or does that really only come into play if it's 10 columns out of a 100-column table?
I think it will very largely depend on your table, on the size of your data, how it's structured. I think you will need to experiment with it a little bit to understand how much benefit you are getting. right? There is benefit, and the benefit is because the columns are not sorted or not indexed in the covering index, and whether that's worth it or not depends on the use case.
Okay, thank you.
Okay, any more questions?
You said that the index, when you need to access all the data from the table, and an index is more or less useless. So my understanding was I might be wrong, that the index is used to look up the position in the table to get all the data. Is that different in Postgres?
So I don't recall the exact percentage, but if you query data from a table that is seeking to retrieve more data than X percentage of the total size of the table, right? Postgres Query Planner will actually resort to a sequential scan even if the column is indexed.
Okay.
Because that's cheaper to execute. You're retrieving that much data anyways. And if your use case is such that you retrieve a lot of data or a major portion of the data from the table anyways all the time, then indexing that column, you're just wasting space. You're not really using it. Postgres will, the query planner will go for a sequential scan in that case anyways. So you're just wasting space.
And can you see that with the on the beginning you had this cost measurement? Can you see it with this?
Yes, yes. So what you will observe is, actually it's a bit. I don't have the slides for it or the database set up for it, but it's a very quick and easy experiment that you can run. Create a table, any table, and put a lot of data in it, indexed by one column. Run a query that retrieves, let's say, 2% of the data, and run an explain plan on it, and then run another query with just the where clause change such that it retrieves, let's say, 90% of the data, and run the explain plan, right? In the first instance, the query planner will show you that it does, it looks up the index, it does the index scan, and in the second instance, even though the column is indexed, it will run a sequential scan. It will show you there.
Okay, thank you. And are the slides maybe available online?
I think so. Yes, I think that once all of this is wrapped up, the SCaLE organizers will make it available on the website.
Okay,
I think
thank
so.
you.
Yeah.
The presentation is also available on YouTube, on SCaLE's YouTube channel. Any more questions?
We have a question there.
This is sort of a general question. Let's say you have Postgres installed from Ubuntu packages right out of the box.
Can you speak a little louder, please, Tim?
General question. Let's say you have Ubuntu installed from, you have Postgres installed from Ubuntu packages right out of the box on a production server. What are you reaching for? And it's a server full SSDs for storage. What are you reaching for first as far as just general performance improvements to make that perform better right out of the box?
So right out of the box, I think that some of the things that you can do is understand what hardware resources are available, right? What memory you want to allocate to the database to use. So right out of the box, you want to understand how many cores you can use for parallel workers, how much memory you want to allocate to shared buffers, to wall buffers. And let's say you've got a ton of memory available, and yet you're allocating only, 12 gigabytes to shared buffers. That would be an underutilization of resources. So those are some of the things that you can do straight off the bat.
Cool.
Okay?
Thank you.
So.
Okay, any more questions? Okay, one more.
Got another one. Partitioning, is that something you can only use when you sort of have a set range for where the data that you're partitioning on will fall in? Like you said, with a year we divide into quarters? Or is there a way to set up a table to be partitioned even as I am continually writing new data to it? I have a log table, say, and I want it to create a 2025 Q1 when it gets to be that time. Is that a thing that works?
Yes, it does. It does. So essentially what you do is you define a rule on how the data is partitioned, and you can define that rule for the data to be routed to the right partition as you insert it as well. So it can be a dynamic rule, right? So
Awesome.
it can be independent of the year. In this particular example, it can be independent of the year. So all months that are January through March will go to Q1 independent of the year. So as you write data, it will go to the right partition.
Thank you.
Okay?
I'm afraid we're out of time, but thank you,
Okay.
Umair.
Thank you very much.